Installing a step-up autotransformer after the main facility transformer presents several issues and potential downsides. The main facility transformer is rated for 500 kVA at 208Y/120 volts. If you install a 160 kVA step-up autotransformer after it, that effectively increases the total load in the main transformer to 660 kVA, which is the original 500 kVA plus the 160 kVA. This can overload the transformer, especially during peak load conditions. The step-up transformer will have its own protection device, either a fuse or a circuit breaker, rated for 160 kVA. If the load in the UPS exceeds that 160 kVA rating, the protection device will trip, and that will interrupt power to the UPS. The step-up autotransformer will alter the voltage regulation of the main transformer. This can lead to voltage fluctuations that go beyond what's acceptable for sensitive loads like the UPS. The voltage regulation of the step-up transformer itself also needs to be considered. Voltage drops or spikes on the secondary side of the step-up transformer can negatively affect how the UPS performs. Autotransformers inherently have harmonic distortion characteristics. The harmonics that are generated by the step-up autotransformer can resonate with the impedance of the electrical distribution system. This can cause voltage distortion and potentially damage sensitive electronic equipment. The impedance and efficiency of the step-up transformer should be compatible with the main facility transformer and the UPS load. The insulation class of the step-up transformer must be appropriate for the voltage levels involved. Before proceeding, a harmonic study should be conducted to determine the potential impact of the step-up transformer on the electrical distribution system. Mitigation measures such as filters or harmonic absorbing transformers may be needed to reduce harmonic distortion. The IEEE 1100.1999, the Emerald Book, advises against using step-up transformers after the service entrance to power electronic load equipment. This is due to the potential for unsatisfactory results. These can include voltage fluctuations, harmonic distortion, and reduced reliability. Based on these issues and the IEEE recommendation, it's generally not recommended to install a step-up autotransformer after the main facility transformer to supply a UPS. Consider alternative options such as firstly, installing a separate transformer for the UPS with a dedicated feeder from the main facility transformer, secondly, upgrading the main facility transformer to a higher capacity, or thirdly, using a voltage stabilizer or a UPS with voltage correction capabilities. When dealing with electrical systems, it is crucial to understand the role and limitations of transformers, including autotransformers. A transformer is a static electrical device that transfers energy from one electrical circuit to another through electromagnetic induction. It typically consists of two or more coils of wire wound around a ferromagnetic core. The coil that receives energy from the source is called the primary winding, and the coil that delivers energy to the load is called the secondary winding. The basic principle behind transformer operation is Faraday's law of electromagnetic induction, which states that a changing magnetic field induces a voltage in a conductor. When alternating current flows through the primary winding, it creates a time-varying magnetic flux in the core. This flux then induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. A step-up transformer has more turns in the secondary winding than in the primary winding, resulting in a high voltage on the secondary side. Conversely, a step-down transformer has fewer turns in the secondary winding, resulting in a lower voltage on the secondary side. Autotransformers are a type of transformer that uses a single winding to serve as both the primary and secondary. A portion of the winding is common to both circuits. This design offers several advantages, including smaller size, lighter weight, and lower cost compared to traditional two-winding transformers. However, autotransformers also have some drawbacks. They do not provide electrical isolation between the primary and secondary circuits, which can be a safety concern in some applications. Also, they have a lower impedance than two-winding transformers, which can make them more susceptible to fault currents. When considering the installation of a step-up autotransformer, it's essential to carefully evaluate the potential impact on the existing electrical system. Overloading is a significant concern. Transformers are designed to operate within a specific kVA rating. Exceeding this rating can cause the transformer to overheat, which can damage the insulation and eventually lead to failure. In the scenario described, adding a 160 kVA step-up autotransformer to a 500 kVA main facility transformer effectively increases the total load to 660 kVA. This represents a 32% overload, which is unacceptable. During peak load conditions, the transformer may experience even higher temperatures, further increasing the risk of failure. Protection devices, such as fuses or circuit breakers, are installed to protect transformers from overloads and short circuits. However, these devices may not always be able to prevent damage from prolonged overloading. Voltage regulation is another important factor to consider. Voltage regulation is a measure of how much the secondary voltage of a transformer changes from no load to full load conditions. A transformer with poor voltage regulation will experience significant voltage drops under load, which can negatively affect the performance of connected equipment. Step-up autotransformers can exacerbate voltage regulation issues. The added impedance of the autotransformer can cause further voltage drops, especially when the load is fluctuating. Sensitive electronic equipment, such as UPS systems, require a stable voltage supply to operate correctly. Voltage fluctuations can cause the UPS to switch to battery power, which can shorten its lifespan. Harmonics are another potential concern. Harmonics are sinusoidal voltages or currents that are integer multiples of the fundamental frequency. They are typically generated by nonlinear loads such as electronic devices, variable frequency drives, and uninterruptible power supplies. Autotransformers can amplify harmonics, which can cause a variety of problems, including overheating of equipment, increased energy losses, and interference with communication systems. The impedance of the electrical distribution system plays a critical role in harmonic distortion. If the impedance is high at certain harmonic frequencies, it can cause resonance, which amplifies the harmonic voltages and currents. This can lead to severe voltage distortion and potentially damage sensitive electronic equipment. To mitigate harmonic distortion, it may be necessary to install filters or harmonic absorbing transformers. Filters are designed to block specific harmonic frequencies, while harmonic absorbing transformers are designed to absorb harmonic currents. The IEEE 519 standard provides guidelines for harmonic limits in electrical power systems. This standard specifies the maximum allowable harmonic voltage and current distortion levels at the point of common coupling between the utility and the customer. Before installing a step-up autotransformer, it's essential to conduct a harmonic study to assess the potential impact on the electrical distribution system. This study should include measurements of existing harmonic levels, as well as simulations to predict the harmonic levels after the autotransformer is installed. Based on the results of the harmonic study, appropriate mitigation measures can be implemented to ensure that harmonic distortion levels remain within acceptable limits. Transformer characteristics also play a crucial role in the overall performance of the system. The impedance of the transformer affects the voltage regulation and fault current levels. The efficiency of the transformer affects the energy losses and operating costs. The insulation class of the transformer determines its ability to withstand voltage stresses. When selecting a step-up autotransformer, it's important to choose a unit that is compatible with the main facility transformer and the UPS load. The impedance of the autotransformer should be carefully matched to the impedance of the existing system to minimize voltage drops and ensure proper coordination of protection devices. The efficiency of the autotransformer should be as high as possible to minimize energy losses. The insulation class of the autotransformer should be appropriate for the voltage levels involved. The IEEE 1100-1999, the Emerald Book, provides recommendations for power and grounding electronic equipment. This standard advises against using step-up transformers after the service entrance to power electronic load equipment. The Emerald Book states that while this can be done in certain cases, it's also possible that less satisfactory results can occur than if the system voltage at the service entrance was used. The Emerald Book recommends considering alternative solutions, such as using a dedicated transformer for the UPS or upgrading the main facility transformer. A dedicated transformer provides electrical isolation between the UPS and the rest of the electrical system, which can improve reliability and reduce the risk of interference. Upgrading the main facility transformer provides additional capacity to handle the UPS load without overloading the transformer. In conclusion, installing a step-up autotransformer after the main facility transformer to supply a UPS can present several issues and potential downsides. These include overloading, voltage regulation problems, harmonic distortion, and reduced reliability. The IEEE 1100-1999 advises against this practice. It is generally recommended to explore alternative options, such as installing a separate transformer for the UPS or upgrading the main facility transformer. When making decisions about electrical systems, it's always best to consult with a qualified electrical engineer. An electrical engineer can assess the specific needs of the application and recommend the best solution to ensure safe, reliable, and efficient operation. Furthermore, any modifications or upgrades to the electrical system must comply with all applicable codes and standards, including the National Electrical Code, NEC, and local building codes. Proper installation and maintenance are essential to ensure the long-term performance and safety of the electrical system. Always use qualified electricians for any electrical work. The NEC provides guidelines for the installation and maintenance of electrical equipment, including transformers. Some key considerations from the NEC include: firstly, transformer overcurrent protection. NEC section 450.3 covers the overcurrent protection requirements for transformers, including the maximum allowable overcurrent device ratings. Secondly, transformer grounding. NEC section 450.10 covers the grounding requirements for transformers, including the size and type of grounding conductors. Thirdly, transformer ventilation. NEC section 450.11 covers the ventilation requirements for transformers, ensuring adequate airflow to prevent overheating. Fourthly, transformer location. NEC section 450.21 covers the location requirements for transformers, including clearances from combustible materials and accessibility for maintenance. Finally, transformer wiring methods. NEC chapter 3 covers the wiring methods for transformers, including the types of cables and conductors that are permitted. In addition to the NEC, there may be other applicable codes and standards, such as those published by the Institute of Electrical and Electronics Engineers (IEEE) and the National Electrical Manufacturers Association (NEMA). It is important to be familiar with all applicable codes and standards before making any changes to the electrical system. Regular maintenance is also essential to ensure the long-term performance and safety of transformers. Maintenance tasks should include, firstly, visual inspections, looking for signs of damage, overheating, or corrosion. Secondly, testing of insulation resistance, measuring the insulation resistance to ground to identify any potential insulation failures. Thirdly, checking for loose connections, tightening any loose connections to prevent overheating and voltage drops. Fourthly, cleaning the transformer, removing dust and debris to improve ventilation. Finally, oil sampling and analysis, testing the transformer oil to identify any contamination or degradation. By following these guidelines, you can ensure that transformers operate safely and reliably for many years. Understanding transformer characteristics and their potential impact on the electrical system is critical for designing and maintaining safe and efficient power systems. Always consult with qualified professionals and adhere to applicable codes and standards to ensure the integrity of the electrical infrastructure. Remember that electrical work can be dangerous, and it is always best to leave it to the experts. Safety should be the top priority when working with electricity. Ensure all power is disconnected before working on any electrical equipment. Use appropriate personal protective equipment, PPE, such as gloves and safety glasses. Follow all safety procedures and guidelines. If you are not comfortable working with electricity, do not attempt to do so. Call a qualified electrician. By taking the necessary precautions, you can prevent accidents and injuries.